Okay, everyone. So last lecture we finished up an example for internally reversible process, and now we're going to move on to analytical form of the Kelvin-Planck statement, and then Carnot cycles, and hopefully finishing up this chapter in really just the conceptual portion of things and a few small examples before we actually start working the examples for this. This next thing that we're going to cover, the analytical form of the Kelvin-Planck statement, it's going to seem a little hairy or messy at first, difficult to understand, but just trust that it'll make much more sense when we actually start working the equations. That's when I find that students actually start picking up things. So rather than try to spend so much time explaining everything on the forefront, we're just going to kind of run through it and let you get these notes. And then when we start working the examples, it'll really start to tie in together. So just trust that you will get it when we finish these examples. So let's see. Oh, I'm still in red. Analytical form of the Kelvin-Planck statement. And let's see. So if you remember, the Kelvin-Planck statement was the one where it had the one thermal reservoir, and then it was impossible to get work out of a system when the only input is from one thermal reservoir. So we're going to start looking into kind of what that means and how we can set that up or manipulate it and make it to where it actually can work. So for any system undergoing a thermodynamic cycle while exchanging energy by heat transfer with a single thermal reservoir. Remember, with a single thermal reservoir, we said that we can't get work out of it. So, oh no, it's frozen again. Shouldn't have erased. Oh man, I don't know why it does this. Okay, reservoir. The net work, so the work of the cycle, and we'll just do that as prime, can never, or really, let's do it this way, can only be negative or zero, never positive. So this is kind of like the unabridged version of that statement. Okay, so I just went ahead and paused it and wrote it really quick. So for any system undergoing a thermodynamic cycle while exchanging energy by heat transfer with a single thermal reservoir, the net work cycle can only be negative or zero, never positive. So remember, that's what it said. This is kind of like the unabridged version of that statement. So the original statement that we looked at said that it was not possible to get work out. And so this supports that. This is a comma. It looks a little off. Just for you guys who are writing your notes down. Okay. So let me draw the little schematic before I write this in an equation to help represent this. So we've got a thermal reservoir. Oh no, oh no, oh no, okay. Oh no, I gotta wait for the pen to catch up. It's gonna erase everything. Okay, so we've got that. And then again, remember the little system that we drew. And this is what we're looking at, right? And of course, this is our system boundary. Right? And then say this is turning this rod right here. So actually, so this is turning this rod. Okay. And we have a weight coming down. And this is a mass, some sort of mass. And so this moving up and down is not possible. That's what this is saying. Why? Because we have a single thermal reservoir. We don't have anything else. And what we're trying to get is some, let's do this in red. What we're trying to get is some heat transfer to help carry this work. So we've got Q. So this is not possible. That's what this is saying. And here is a formula to help illustrate what this all is saying. Okay, so the work of the cycle is less than or equal to 0. Okay, so 0 internal irreversibilities present. Okay, and then equal to 0 are no internal irreversibilities. We'll kind of put this into motion later. Okay, and then again, this is for single reservoir. Okay, and then let's pick up another page. So now we have the applications to power cycles interacting with two thermal reservoirs. So we know that it's not possible with one. We're only going to have negative or 0 work for the cycle. So let's see what we can do with 2. So applications to power cycle interacting with 2 thermal reservoirs. Okay. And then for a system undergoing a power cycle while communicating thermally with 2 thermal reservoirs, a hot reservoir and a cold reservoir, the thermal efficiency of such cycle is, and I'm going to give you this equation. So let me just write this down for you. But this is what we're doing. A system undergoing a power cycle, moving into power cycles, while communicating thermally with 2 thermal reservoirs a hot and cold reservoir, the thermal efficiency of such cycle is, and here's that formula. We denote it with work of the cycle over hot heat transfer equals 1 less heat transfer cold over heat transfer hot. Okay, and so let's draw this out because I feel like drawing them helps a lot, especially before we start really working them. It just kind of helps you picture what we're talking about because they do get really wordy. I'm a big fan of drawing your schematics, and just to let you know that even if you don't get a question right on the exam, I'm a huge fan of partial credit. And the only time that you get no partial credit is when you leave it blank. So at a minimum, and I require schematics to be drawn. Here's the cold reservoir, by the way. I require them to be drawn, but at a minimum, draw the things that you know and write the things that you know so that I can at least see that you've got something going on. Even if you don't fully understand or know, how to answer the question, I at least know that you're in the class, right? I'm taking notes. So I feel like that's worth something. So we've got some hot heat transfer here. And let's do this in blue. So we've got some heat transfer out into cold. And then what it is saying is that, let's do it in rainbow. Because why not? That's why. Because apparently when I want to write with the rainbow pen, it crashes. But, we don't give up. Okay. So then we have the work of the cycle equal to heat transfer hot less heat transfer cold, right? So the difference, whatever we've got coming in right here, whatever we've got coming in less coming out is what we've got for our work. So that's wonderful that we can, kind of understand why just having one thermal reservoir is not going to produce anything. And then why, obviously, if you have two thermal reservoirs, hot and a cold, that you can actually get some work out of it. But what does this actually mean? How can we apply this? So we have three applications. Applications to power cycles. So we're talking about power cycles. Interacting with two thermal reservoirs. Okay, and so by applying the Kelvin-Planck statement of the second law, we can draw these three conclusions. So by applying by applying the Kelvin-Planck statement of the second law. And what is this equation? I wrote it down. Let me see. Okay, I went back. So here's this equation. And this was the work cycle less than 0, right? And then it's where less than 0 is internal irreversibilities. I'll just abbreviate that, present. And then equal to 0 is no internal irreversibilities. Okay, so that's this equation. Okay, so by applying the Kelvin-Planck statement of the second law, so that's this, 3 conclusions. Can be drawn. Okay, so the first one, we'll do in red. The value of the thermal efficiency must be less than 100%. So let's talk about this. It makes sense, but if you are still having trouble with this, let's think about this. The value of the thermal efficiency must be less than 100%. Why? Why should this efficiency be less than 100%? First of all, we know that nothing is 100% efficient, right? But then also, because when you're talking about 2 thermal reservoirs and you have that heat transfer hot coming in, and then you're using some to create that work for the cycle, and then some of that heat transfer cold is coming out, then you know that you're not going to be 100%, right? You're going to have some loss, whether it be due to friction from what's moving inside of your system, or just how well your system is insulated. Maybe it's just going into the atmosphere. So there's a number of different ways that you can lose this efficiency. So that's why we can draw this conclusion. The value of the thermal efficiency must be less than 100%. And so we can go on further to say, we can go on further to say only a portion of the heat transfer QH can be obtained as work, and the remainder QC is discharged by heat transfer to the cold reservoir. Okay, this should also help clue you in to why that original statement that we talked about, where the Kelvin-Planck statement, so that's why the original statement of the Kelvin-Planck that you can't extract a positive work from one thermal reservoir is because no system is 100% efficient. How can we put, how can you put 50 of, whatever you're using? Say you've got 50 coming in from that thermal reservoir, whatever units you're using, and you're going to try and work that into work coming out of your cycle. Something has to leave somewhere. So that's what that original statement is saying, is it's saying, hey, whatever you put in cannot come out. We can't have 100% efficient system. So there has to be another thermal reservoir. That excess heat, that unused heat, has to go somewhere. That heat that's burned off from friction or from where you have your manufacturing plant located, or whatever scenario you're working with, there is going to be some sort of heat loss there. And we have to account for that. And we account for that using this second thermal reservoir. So the next 2 conclusions that we can draw are called the corollaries. And those are, let's see, 2 and 3 are Carnot corollaries. Let's just see if we can put that on the same page. maybe zoom out. Nope, it's just not going to let me. There it is. Just drag it that way. Okay. Okay. And so these are, let's see, Carnot corollaries. So here's these other two conclusions that we can draw. So it is, well, really it's one of two for Carnot, but overall it's 2 and 3 of the 3 conclusions. The thermal efficiency of an irreversible power cycle is always less than the thermal efficiency of a reversible power cycle when each operates between the same 2 thermal reservoirs. Okay, so this should feel like common sense for you, right? So we've got 2 identical setups, and if we're comparing and contrasting, and we've got the thermal efficiency of an irreversible power cycle is always less than the thermal efficiency of a reversible power cycle. This should be common sense to you because of what we understood about reversible power cycles. Reversible power cycles are only idealized. They are the very best case scenario. There is nothing going to be more efficient or better or a better option than a reversible power cycle. So therefore, everything else, whatever we compare to this reversible power cycle, is going to be less. So therefore, the thermal efficiency of an irreversible power cycle is always less than the thermal efficiency of a reversible power cycle. So that's the other conclusion that we can draw. And then the last 3 out of 3 conclusions, but 2 out of 2 Carnot corollaries are all reversible power cycles operating between the same 2 thermal reservoirs have the same thermal efficiency. And this should also sound like common sense, even if you can't quite put the words of why together. So let's just read it again. All reversible power cycles operating between the same 2 thermal reservoirs have the same thermal efficiency. That's because our thermal efficiency in regard to a reversible power cycle or a reversible whatever you're looking at is always going to be idealized. So it's always going to be the best case scenario. It's going to be 100%, right? Reversible, nothing impacting on its surroundings, no loss, no heat loss, nothing like that. So this reversible power cycle is 100% efficient. So therefore, when we're comparing reversible to reversible, they're going to be equal because they're both the best case scenario. And again, I'll write this down actually because, let's see. Okay. Let's make it a little bit smaller. Okay. a cycle, even though you guys know this, a cycle is considered reversible when there are no irreversibilities within the system as it undergoes the cycle and heat transfers between the system and reservoirs occur reversibly. So just a note for you guys on that. Okay, so let's move into refrigeration and heat pump cycles, and here are some applications for those. Applications to refrigeration and heat pump cycles. Interacting with two thermal reservoirs. Okay. So just a little excerpt. For a system, I'll just pause and write that. Okay, so applications to refrigeration and heat pump cycles interacting with two thermal reservoirs. For a system undergoing a refrigeration cycle or heat pump cycle while communicating thermally with two thermal reservoirs, a hot reservoir and a cold reservoir. So let's draw that schematic really quick here. Okay, just the same one that we've been using, just so that we can keep it consistent. Again, we've got our system, drawing this boundary here. You've got a hot reservoir and a cold reservoir. And then you've got see. Let's just do this. Okay, so why is this schematic drawn in this way? Well, because remember, hot naturally flows from hot to cold, right? That's how the thermal law works. And so when we're looking at a refrigeration, we know that we can't cool something down without there being work from a system. So that's why it's going in reverse. It seems to be going in reverse from the natural law, and that's because that's what it is. That is what's happening. So we have two coefficients. So that is our schematic. And then you've got the coefficient of performance for the refrigeration cycle is, let's see, heat transfer cold, work of the cycle, heat transfer cold over heat transfer H minus heat transfer cold. So you can see that over here. And then again, so this is the refrigeration, and then and for the heat pump cycle is, this will help out a little bit, cools hot, work the cycle. So you should see where we're just flipping these. SQC. We're just highlighting heat transfer cold or the hot heat transfer. So you've got both of these equations. So let's move on. So we also have three conclusions that we can draw from this Kelvin-Planck statement equation. So let's go ahead and write these down. So three conclusions. Whoop. That looks rough. Okay. Three conclusions. And I'll just pause and write. Okay, so here are the three conclusions. I've noted them as 1, 1A, and 2 because 1A is related to 1. So 1, for a refrigeration effect to occur, a net work input work cycle is required. Accordingly, the coefficient of performance must be finite in value. So let's just briefly go over what the coefficient of performance is. It is the ratio of useful heating or cooling provided to work required. So 1A, the coefficient of performance of an irreversible refrigeration cycle is always less than the coefficient of performance of a reversible refrigeration cycle when each operates between the same two thermal reservoirs. Completely makes sense. We've gone over this quite a few times, but if a lower coefficient of performance equates to higher efficiency, then the performance of an irreversible refrigeration cycle is always going to be less than the coefficient performance of a reversible refrigeration cycle in terms of efficiency. So it's going to have less of an efficiency. And then 2, all reversible refrigeration cycles operating between the same two thermal reservoirs have the same coefficient of performance. So that is really important to note in this conclusion. All reversible refrigeration cycles operating between the same two thermal reservoirs have the same coefficient of performance. And again, that makes complete sense because reversible refrigeration cycle, anything that's reversible, is going to be the best that it's ever going to be. Therefore, you're not going to have a better best, right? Or a less best when you're speaking in terms of reversible when you have the same parameters to consider. And then just a note at the bottom, all three conclusions also apply to a system undergoing a heat pump cycle between hot and cold reservoirs. So just kind of further defining those parameters. So let's move on to the Kelvin temperature scale, and we're going to talk a little bit about those heat pump cycles, power cycles, refrigeration cycles, exchanging energy by heat transfer with a hot and cold reservoir. And just for time, I'm going to be pausing these and writing all of the notes and then going over them. Okay, so let's go over this. So consider systems undergoing a power cycle and a refrigeration or heat pump cycle, and each while exchanging energy by heat transfer with hot and cold reservoirs. So that's wordy. Let's go ahead and just draw it out really quickly, and then I'll give you the formula, and then we will move on and talk further about it. Oops. Go. Same more thing. And again, I find it extremely valuable to draw out what you are dealing with. So hot reservoir, so that you can get a mental picture of what's going on. Because these are the types of things that you could be dealing with in your future job. So if we have QH coming down, and then we have heat transfer cold coming down, then we have work of your cycle equals QH minus QC. So you can see that here. And again, just if you want to see it, this is your boundary. This is your defining area. Okay, so if you have QH coming in from that hot reservoir and then QC coming out into the cold reservoir, then what's coming out, your work cycle, the work of your cycle is your QH minus your QC. And then if you have kind of just the opposite, if you have a forced QC going in and then you have a QH, this QH would then equal QC plus work cycle. And then you have just the opposite. You have work coming in, right? And so you have QH minus QC. And again, this is just your boundary. And why is it the opposite? We've kind of gone over that, and this is taken into account this Kelvin-Planck statement and these other statements of the second law, so that heat naturally flows from hot to cold, right? So you have a natural flow here. And so then naturally you will have work produced from what is the difference between QH minus QC. That's the work that you're getting out of here. Whatever's coming out of here, and then whatever's left over coming out. But if you're trying to do the opposite, right? So if you're trying to do cold to hot, well, then you're going to have to input some work from an external force to get that cold to force naturally on the hot reservoir, because we know that the natural law is the heat flows from hot to cold. So then you will have QH minus QC. So we will have some work coming in to force that cold reservoir, that cold heat transfer into QH, which would then make your QH what you originally started with as QC plus your work cycle. So all of this coming up to help that go into the hot reservoir. And here's an equation for you. Let's see. The Kelvin, let me just write a note. The Kelvin temperature is defined so that, let's see, QC over QH, so heat transfer cold over heat transfer hot of a rev cycle equals temperature cold over temperature hot. Pretty self-explanatory. Let's get into that. So referencing this formula up here, when cycles are reversible, and only then the ratio of the heat transfers equal the ratio of the temperature of the Kelvin scale, where TH is the temperature of the hot reservoir and TC is the temperature of the cold reservoir. And then just another little note, you know this, but it kind of helps you have a big picture of how we determine and how the first and second law actually determine and build thermometers is as temperatures on the Rankine scale differ from Kelvin temperatures only by a factor of 1.8, which here's that conversion. The T's in the above equation may be on either side of the temperature. This equation is not valuable for temperatures for Celsius or Fahrenheit, and these do not differ from Kelvin temperatures by only a factor. So right here, this is how we get our factor of 1.8, this linear. And then these obviously don't work. It's not the same because we just do a factor. So this right here is a big player in why we have things like thermometers. Okay, so for maximum performance measures for cycles operating between two thermal reservoirs, we can deduce the following from the Kelvin-Planck statement. And these we've gone over quite a few times. Number one, thermal efficiency of an irreversible power cycle is always less than the thermal efficiency of a reversible power cycle when each operates between the same two thermal reservoirs. Number two, coefficient of performance of an irreversible refrigeration cycle is always less than the coefficient of performance of a reversible refrigeration cycle, again, when each operates between the same two thermal reservoirs. And then lastly, the coefficient of performance of an irreversible heat pump cycle is always less than the coefficient of performance of a reversible heat pump cycle, again, when each operates between the same two thermal reservoirs. And then you can see from all of those that it follows the maximum theoretical thermal efficiency and coefficients of performance in these cases, and then are achieved only by reversible heats or reversible cycles, whichever one you're using. And then because of that, we can use these respective formulas. So we have a power cycle. Okay, and so this power cycle, we've got the max equals 1 minus Tc over Th. And then we have refrigeration cycle. Okay, max equals Tc over Th minus Tc. And then lastly, heat pump cycle, as well as the max Th Tc minus Th over Thtc. And just a note here to point out that when using these, Th and Tc must be on the Kelvin Rankine scale. Okay, so let's work a really easy problem. This entire problem will be one step in the examples that I work after you watch these videos. So power cycle analysis. A system undergoes a power cycle while receiving 1,000 kilojoules by heat transfer from thermal reservoir at a temperature of 500 Kelvin and discharging 600 kilojoules by heat transfer to a thermal reservoir at A, 200 Kelvin, B, 300 Kelvin, C, 400 Kelvin. For each case, determine whether the cycle operates irreversibly, operates reversibly, or it is impossible. So I went ahead and drew out the hot reservoir with a temperature of 500 Kelvin. We know that it's going through a power cycle. And then we have a cold reservoir with a cold temperature of each case respectively, A200, B300, and C400 Kelvin. And then what we know is that we have a heat transfer hot, which is going to be 1,000 kilojoules. And then we have a heat transfer cold, which is 600 kilojoules. And then we have, because of this flow, we know that we have work coming out in a work cycle. And then here is our boundary. Okay. So the solution to work this is basically to determine the nature of the cycle, compare actual cycle performance, which let's write this. Ooh. Okay. So again, we need to determine the nature of the cycle, comparing the actual cycle performance, which is N, not to be confused with N for polytropic, but so this is actual cycle performance with N max, which is the max, again, maximum theoretical cycle performance. There you go. And we're using those formulas that we just wrote, but I'll go ahead and write them again. So first, of course, if we are, let's come up here and bring that down a little bit. If what we're trying to do is compare N to N max, then we need to calculate both of these. So for actual performance, we get N equals 1 minus QC over QH equals 1 minus 600 kilojoules over 1,000 kilojoules, which is going to give us 0.4. Okay, so that's that. So then after we calculate the actual performances, we need to go and do our maximum theoretical performance so that we can compare it to our actual performance. And so that'll be our max equals 1 minus TC over TH equals 1 minus 200 Kelvin over 500 Kelvin, which equals 0.6. And then N max equals 1 minus TC over TH again, which equals 1 minus 300 Kelvin over 500 Kelvin, which equals 0.4. And then N max equals 1 minus TC over TH, which is 1 minus 400 Kelvin over 500 Kelvin equals 0.2. So you see how it says that we can only use Kelvin in these instances when we're doing these comparisons, because we're comparing it to kilojoules over here and we have Kelvin. So we need to make sure that we're using Kelvin when we're doing these comparisons so that we can compare the outputs, these ratios, to each other. So then what we have for each case, because this is case A, case B, and case C, what we have is that 0.4 right here, which is our actual performance. So N equal to 0.4 is less than our N max of 0.6, which equals irreversible. Okay, and then we have 0.4 equals 0.4, right? Because our 0.4 equals 0.4, and that is reversible. And then we have 0.4, which is our actual performance, is greater than 0.2, and then that is impossible. Okay, and remember, why are these irreversible, reversible, and impossible? Because our actual performance, which is 0.4, and then we're comparing it to the maximum theoretical performance. So if we have our maximum theoretical performance of 0.4, and then our actual performance is 0.4, then that's a reversible system, right? That's the max that we're ever going to get. That's the best case scenario. But if we have a maximum theoretical performance of 0.2 and then an actual performance of 0.4, then that's impossible. We're not going to be able to have actual cycle performance become greater. We're not going to have a greater performance of actual performance over our theoretical performance. And then when we have 0.6 as our maximum theoretical performance, and then our actual performance is 0.4, then that's reversible. We know that, irreversible. We know that that is possible, right? So we know that, hey, our actual performance is less than our maximum theoretical performance because we cannot go any higher than 0.4, and that is reversible Because we are less than that in terms of performance, then we know that that is irreversible, because we know that everything that's not reversible is either irreversible or impossible. So let's move on to the Carnot cycle. This provides a specific example of a reversible cycle that operates between two thermal reservoirs. And in a Carnot cycle, the system executing the cycle undergoes a series of 4 internally reversible processes, 2 adiabatic alternated with 2 isothermal processes. So in the first lecture that I posted, hinting on, hey, reversible is not really possible, but we do kind of talk about internally reversible processes. That's because when we start talking about the amount of entropy that is expelled during a process, it's so minutely small that we differentiate that from irreversibility by saying that it is reversible. It's so small that we're just going to consider it reversible, right? So the difference between a regular cup full of ice and a thermos full of ice, well, we know that that thermos is not 100% isolated, but the amount of waste compared to a regular cup is so small, or the amount of entropy, right, generated, ice melting is so small, the rate is so small, that we're going to go ahead and consider that isolated, even though we know that it's not 100% isolated. So here's the schematic drawn of a piston cylinder, gas in a piston cylinder executing a Carnot cycle. So what you have is you have this gas that is the adiabatic compression, and underneath it is the insulating stand. So that's where we have Q equal to 0. And then we have this expansion, isothermal expansion, and we're having some hot heat transfer coming in from the hot reservoir underneath. And then we have, again, adiabatic expansion where that insulating stand comes back into play and there is no more heat transfer. And then the isothermal compression, which is QC when we go back into that cold reservoir underneath. And this process is a cycle, so it's going, this isothermal compression is going into adiabatic compression. And then I've shown that on this PV diagram where we start at 1 and we're going up the pressure, and then from 2 to 3 we're going on that constant temp line, but we're going down in pressure as well. And then 3 to 4, we're going to temperature hot, temperature cold, also down in pressure, and then back around for a complete cycle. So the PV diagram and the schematic shown here is of water executing a Carnot cycle through 4 interconnected components shown below. So right here, let's go here. Yeah. So we have our hot reservoir with our heat transfer coming into our boiler, and then the boiler is sending through to the turbine that is expelling work, and then whatever is left is coming down in here to a condenser, which is going into a cold reservoir with a heat transfer, of C. Sorry about that. And then coming out through the condenser, coming into a pump, which is also receiving work, right? Because right here we still have cold. This is cold. And we're trying to get it to hot, right? We're trying to get it here, but what we have coming out is cold. So we need some more work to come into this pump to pump the cold into the boiler so that we can get it to go from cold to hot. And then it just keeps going around in the cycle. So over here, if we have our PV diagram with our constant thermal lines, then what we have is we have, right over here, we have state 1, okay? And then it's coming down to state 2, and then state 2 is coming over on that cold line, to state 3, and then that is coming up to state 4, and then 4 is rounding back around and going to 1. So here we have that boiler. We're at 1, we're coming down, 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 going through to 2 when we're getting that, when we're starting to use that condenser, and then we're coming back up to this hot temperature by way of work coming into the pump when we're getting into 4, and then we're going back around for these processes of 1 through 4. And here's where they are. So we have 1 right here. So we're starting in between there and that hot. And then we have 2 when we start to cool down. And then we have 3 when we're cooled, but we're now coming through the pump to get back up to hot, which is 4, and then back around. And so each of these cases, the thermal efficiency is given by this formula. So let me just write it down. So thermal efficiency, just give this formula again. So it's the max, we just worked an example, equals 1 minus Tc over Th. And this is how you would get this thermal efficiency. So what happens when we have a refrigeration cycle or a heat pump cycle? Because what this cycle is currently showing us is the natural flow of heat, right? Flowing from something hot to cold and then using that pump to accept work to pump cold back into hot. But what if we have something like our refrigerator that we want cooler than the room temperature? So we can't allow the natural heat transfer to take place and just get it to room temperature until all of the exchanges have ceased, right? So we want it colder. We want to force it to be colder. So basically, let me just write this down in red. Okay, so Carnot refrigeration and heat pump cycles. So for this, 3 things kind of occur. So it is operated in opposite direction. Magnitudes of energy transfer remain the same. However, energy transfers are oppositely directed. So it's the same thing, we're just really doing the opposite. And then we refer to these obviously as the Carnot refrigeration and heat pump cycles, and we can give the coefficient of performance for those separately. And so these equations, let's see, coefficient of performance. So we have the refrigeration, and then we have the heat pump. And so to get those, what we would get, we looked at these earlier. And I'm just going to write them down here since we're discussing them again. And then we have the max here. It's TH over TH minus TC. So let's talk about the Clausius inequality. This provides the basis for developing the entropy concept that we will discuss in chapter 6. We've kind of already started discussing it, but since this is jumping a little bit ahead into chapter 5, which is where we are discussing the second law, entropy is more covered in chapter 6. The Clausius inequality is applicable to any cycle without regard for the body or bodies from which the system undergoing a cycle receives energy by heat transfer, or to which the system rejects energy by heat transfer. Such bodies need thermal reservoirs. And the Clausius inequality is developed from the Kelvin-Planck statement, second law, and can be expressed as, and here's the equation, where that first integral is to be performed over all parts of the boundary and over the entire cycle. So you see that little circle in there to denote that. And then this B subscript indicates the integrand is evaluated at the boundary of the system executing the cycle. And then just down here, the nature of the cycle executed is indicated by the following value of the cycle. And here it is, if it's equal to 0, then no irreversibilities present within the system. If it's greater than 0, then irreversibilities are present within the system. And then if it's less than 0, then it is impossible. So I think we're just going to do one short example, just showing you these equal to, greater than, and less than, and then we will wrap up the lecture portion of this chapter. So here's the example. A system undergoes a cycle while receiving 1,000 kilojoules by heat transfer at a temperature of 500 Kelvin, and discharging 600 kilojoules by heat transfer at A, 200 Kelvin, B, 300 Kelvin, C, 400 Kelvin. What is the nature of the cycle in each case? Also, just a note, all of these are in Kelvin, and remember they need to be in Kelvin. So if they're not, you would need to convert them. So the solution, we would need to use these equations that we just highlighted above or before so that we can see what the nature of each cycle. So we're just comparing them, right? So what we have is, instead of finding what the max is or what the actual is and then comparing the maxes to them to see if they're reversible, irreversible, or possible, what we're going to do with these inequalities is just compare them to 0. So if we have a case, which is a negative cycle, equals 1,000 kilojoules over 500 Kelvin minus 600 kilojoules over 200 Kelvin, then what we end up with is -1 kilojoule Kelvin, which is equal to +1 kilojoule Kelvin, which is greater than 0, which means irreversibilities are present. And let me just write down this formula again for you. Let's see. Just so that you can see how it all works out. So we wrote down this formula, but this is actually how it all ends up. H minus Q out over TC, and then that equals the cycle, the negative cycle. Okay, so we have that, and then we have B, which again, we're just going to plug in our values. I think that's on your formula sheet, but if not, I wrote it down again for you. Kelvin minus 600 kilojoules, 300 Kelvin, which equals 0 kilojoules Kelvin, which is equal to 0. And then that means no irreversibilities are present. So it's staying the same thing, just in or same measuring as what we did before, where we were comparing it to actual performance, but here we're just comparing it to 0. And so then for the last case, which is C, we're just going to write down our formula again, plugging in. That's 4. Sorry about that. 400 Kelvin. 0.5 kilojoules Kelvin, which is less than 0. And then because this is a negative, sorry about that, because we have a negative cycle right here. So this is a negative 0.5, which is less than 0, which means that this is impossible. Okay, so that's the end of this. We have some examples and probably some more examples next week. So just keep referring back to this if you're not sure why we're doing something in the examples, but I do try to explain a little bit along the way also when I'm working these problems as well. All right, thank you.